So hello everyone, welcome. So we are going to start a PYQ solution series and we are going to start from quantum mechanics. So in this lecture, we will be solving around 10 questions uh, which are listed here, and the PDF of the same you will be finding in the corresponding folder within the course. So let's just start. So in the first question, we are going to uh, derive Bohr's angular momentum quantization condition in Bohr's atomic model from the concept of de Broglie waves. So it is a PYQ from 2010. So each question will be in three particular sections, which are introduction, solution, and conclusion. So introduction says that Bohr's atomic model introduces the concept of quantized angular momentum for electrons which are orbiting the nucleus. Okay. So this concept is fundamentally linked to the wave nature of electron. Okay. So in broader way, we can say that it is linked to wave nature of matter. Okay. In general, we could say that it is wave nature of matter, and we know that before this, Planck, Einstein, and Compton. Planck, Einstein, and Compton established particle nature of radiation. Particle nature of radiation. So we all know that nature loves symmetry, and this is the converse of that, that you are finding the radiation nature of particle or wave nature of particle. So according to de Broglie, the wavelength of an electron is given by lambda equals to h upon p. We all know that h is Planck's constant and p is nothing but momentum. Okay. So what was the hypothesis that for an electron in circular orbit of radius r, the circumference must be an integral multiple that equals to 0, 1, 2, 3, and so on, integral multiple of the de Broglie wavelength, and this is what is the mathematical relation, that 2 pi r is circumference and n lambda is the integral multiple of wavelength. So for lambda you could substitute h by p, and for p you could substitute mv, and when you bring mv in left hand side, then you will get mvr equals to n h upon 2 pi. This mvr is nothing but angular momentum. So from here you can simply write the reduced Planck's constant. Okay, h bar is nothing but reduced Planck's constant, which is h upon 2 pi. So this is the condition which is the actual angular momentum quantization. That is, angular momentum could take only definite values, not the continuous values. What definite values? Either it could be 0 or h bar or 2h bar, 3h bar, and so on. But it could not be anything in between 2h bar and 3h bar. This is what we have learned, and this is what this is what we get the behavior of the matter or particles at atomic scale. Okay, that their angular momentum cannot be continuous; it must be discrete, and this is the relation from wave nature of matter. Wave nature of matter. And let me tell you, this particular topic has attracted a lot of PYQ in past, in almost all the examination of UPSC. So the conclusion is that Bohr's quantization of angular momentum provides a fundamental insight into discrete nature of atomic energy levels, leading to explanation of the atomic spectra. So let me tell you, this atomic spectra is nothing but the lines which you see when you do the spectroscopy of atoms or elements. So this also leads to a spectroscopy, scopy, which you will study in atomic and molecular physics. Atomic and molecular physics. Okay, so let's move to the second question. Here we are required to calculate the wavelength of the de Broglie waves which are associated with electrons accelerated through a potential difference of 200 volt. Okay, so this is pretty simple question. Whenever you accelerate the electron, you get kinetic energy. From kinetic energy, you can get the momentum. and from momentum you can get its corresponding wavelength. Okay, so this is what you have to calculate. So we all know that the introduction goes as follows, that the concept of de Broglie wavelength states that particles also behave as a wave whose wavelength can be calculated when they are accelerated by a known potential difference, because let's improve it, because they gain kinetic energy when accelerated, and when they gain kinetic energy they do have momentum, and when they do have momentum they will have certain kind of wavelength associated with it. So the kinetic energy gained by electron is EV equals to half mv square. This EV is nothing but charge times potential difference. Kinetic energy is equal to work done is equal to charge times potential difference. We get it from the electrodynamics. We get it from electrodynamics. And this is and half mv square is the classical version of kinetic energy. So we all know that E is nothing but the electronic charge. V is the potential difference. In our case, it is going to be 200 volts. So here we have expanded it, but I think if you know the direct formula, which we use in exams like IIT JAM, then you can simply use lambda is equal to 12.3 divided by half under root V angstrom. A straightforward answer. But those who those who have done or cleared the examinations like JS, NET, JRF, IIT JAM, okay, so you must have been aware of this formula. Okay, this is the simple formula, but this is the descriptive examination, and here we have certain procedure to follow. Okay, and we must follow that. So when we rearrange, we get this particular form for velocity, which is under root 2 EV upon m. Okay, and we have just got it from this particular uh, expression. Then we all know that de Broglie wavelength is given by h equals to lambda equals to h by p, and p is nothing but mv. And here you can plug in the value of v, and finally you will get lambda equal to h divided by under root 2 mev. And when you calculate this, simple thing is this, or what we have just wrote here. Okay, this is simply 12.3 under root v angstrom in its reduced form. So it is ready to use form, and here you will plug each and every formula and you will get the answer directly, which is around 8.6 multiplied by 10 to the power minus 12 meters. So the conclusion goes as follows: the wavelength of the de Broglie waves associated with electrons accelerated through 200 volts is approximately this much, which highlights the wave nature of electron at the atomic scale or quantum scale, whatever you like to write. Okay, so I think we understood the concept pretty well, that what is the difference when you solve for objective examination like JEST, NET or IIT JAM, and when you do it for the UPSC where you have to do it subjectively. So there is not much difference. Okay, you just need to be appropriate with your mindset and you will get it done. Now let's solve another question where we are going to estimate the size of hydrogen atom and the ground state energy from the uncertainty principle. This question is from 2012. So here we are going to estimate the characteristic size of hydrogen atom and its ground state energy using the Heisenberg's uncertainty principle. So what we are going to do, we are going to model the electron bound to the proton by Coulombic attraction forces. Okay, and then we will apply the quantum mechanical uncertainty relation to that particular Coulombic attraction force expression, and then we can find radius and minimum energy of the electron in its ground state energy with some mathematical manipulation. Let us learn that what is that mathematical manipulation, which will help you to solve this PYQ and another similar PYQs as well. So We estimate the electron's positions uncertainty as the size of the atom r. So suppose, how do you describe the size of the atom? So I am asking description of the atom. Like if I tell you, okay, we have one particular atom, then how could we describe the size of the atom? So there are various ways. The first way is to write its radius. The second way is to write its diameter, which is essentially the same information at that small scale. Like multiplying 2r is not um, going to create much uh, difference when compared to r. Then you can also describe the mm, that particular atom with its surface area or volume, whatever. But at the essence, we have the radius only. Whatever is circular or spherical in approximation, radius is the best way to describe that. Okay. So whenever we ask to find the uncertainty, like you are going to calculate the radius, then what could be the uncertainty in your calculation? The answer is the uncertainty could be anything, but its magnet order would be approximately same. So what do we mean by order? So suppose you have nucleus of size 10 to the power minus 14 meter, and you are going to calculate the same thing. So what could be order? So order would be approximately equal to this particular value only. So it would be same 10 to the power minus 14, and this is going to be your uncertainty as well. So this is the basic assumption, approximation, whatever you want to say, that your error in measurement would be same as of the size of the atom. So in this case, in our uncertainty relation, which is delta x multiplied by delta p in the same direction as of x would be always equal to or greater than h bar by 2. So this delta x would be approximately equal to the radius of the atom itself. Okay. And look, this is the necessary minimum condition. So from our various previous effort, we have found that this particular equation fits best for the hydrogen atom. Okay. Then you are saying, okay, so we have the original expression as delta x times delta px greater than h bar by 2. Then why we are removing this particular 2? Why are we using this form? So I am saying that let's understand Heisenberg's uncertainty principle. It is a condition. It is not a mathematical formula. So as long as this greater than sign is valid, we are correct. So that is why this is correct. So now delta P would be simply h bar upon r, where r is the radius of the atom. And same thing you could assume for the momentum as well, that uncertainty in the measurement of the momentum would be equal to or approximately equal to the momentum itself. So in that way, we could calculate the kinetic energy, which would be momentum square divided by 2 times mass of electron, or this particular expression. And we all know that potential energy, because now we need to write the energy equation. So to write the energy equation, we need to find the kinetic energy and potential energy. So kinetic energy is nothing but momentum square upon 2m and this potential energy is nothing but 1 upon 4 pi epsilon 0 charge 1 charge 2 divided by the r. Okay. So we know that it is hydrogen atom, then it would be it would be minus E for electron, and it would be plus E for the part of the nucleus, that is proton. And this is the distance between them, the radius itself. And when you do it, you will simply get this particular expression. And why we are getting to know the energy equation? Like, why do we need to find it? The answer is simple, because we are required to find the ground state energy. Now, this is very simple to assume that if something is in its ground state, then it would be minimum. It would be minimum. That means whenever you differentiate with respect to r, you are going to get 0, provided that its double differentiation is greater than 0, which is also true. We will write that equation, provided that double derivative of energy with respect to the radius is greater than 0, so it is minima. And minimum energy would be the ground state energy. So now you got one mathematical equation which will simply yield you the radius. This is the value of the radius. So whenever you calculate that, you will simply get 0.529 angstrom. And this is what we also call Bohr's radius. Okay. So you substitute all the values, we calculate, and you will get this particular value, which is around 0.52 or 53 when you round off when we round up angstrom. Angstrom means 10 to the power minus 10 meter. So this is approximately equal to Bohr's radius. Now when you substitute this particular value of R back to the energy equation, you simply get the value of ground state energy, which is 13.6 minus 13.6 electron volt. Okay. So conclusion is simple, that uncertainty principle, we estimate that size or radius of the hydrogen atom is going to be 0.529 angstrom, that is Bohr's radius. The ground state energy would be simply minus 13.6 electron volt. And these estimates agree remarkably well with the results from the full quantum mechanical treatment of hydrogen atom, which illustrates the power of the uncertainty principle in deriving the fundamental atomic properties. Okay. So Heisenberg's uncertainty principle is a very powerful mathematical statement and not a formula. It is a mathematical statement which restricts the precision of two quantities uh, which are conjugate pairs, and they cannot be measured with infinite precision at the same particular moment. So now let's move to this next question. We are required to use the uncertainty principle to estimate the ground state energy of the linear harmonic oscillator. Awesome. This is again the same question. The only difference is that in the normal hydrogen atom, you will have potential energy equal to 1 upon 4 pi epsilon 0 charge 1 multiplied with charge 2 divided by distance in between charge 1 and charge 2. So this is the potential in the case of Coulombic, and we all know that kinetic energy is going to be P square upon 2n. Okay. So this is the general structure, but for the linear harmonic oscillator, we have potential of this form, half kx square. And so again, we have energy in this form, that the first term in the right hand side is nothing but kinetic energy, and second term is potential energy. Now the same procedure we are going to form, that we will set up the Heisenberg's uncertainty principle. We will find the interrelationship in between momentum and displacement. Okay. And then we will substitute that particular into this energy equation. So we know that delta x times delta p is greater than h bar by 2. And again, we set up the approximation that the uncertainties in the measurement of p and x is going to be of the um, same order. So delta p would be approximately equal to p, and delta x would be approximately equal to x. This is what we are going to begin with. So from here we have got that p is approximately equal to h bar upon 2x this time. So great. So again, we are going to minimize E with respect to X, because we are going to find ground state energy. Okay. So whenever you differentiate that, we will get this particular expression, and it is pretty simple to solve this all. Not a big deal. You are just going to differentiate it. So this is class 11th level mathematics. And we are going to write one missing statement here, that also double derivative of energy with respect to X is greater than 0. Hence, we are calling it minima. Okay, so now when you put back the value of x square back to the equation of energy, you are going to find that energy is nothing but half h bar omega upon 2, where omega is nothing but under root k by m. So we could finally say that the ground state energy of a linear harmonic oscillator is h bar omega upon 2, and it demonstrates the 0 point energy due to the quantum fluctuation that even in the ground state, it might be expected in classical physics that the energy should be zero, but energy is not actually zero. And because of the 0 point energy, the position and momentum of the oscillator in the ground state energy are not fixed. Okay. And they have the small range of the variance, and that follows the Heisenberg's uncertainty principle. So this is what we have solved till now. So I hope this is pretty clear to you all. Now let's move to the next question, and we are going to solve this question. So this question is also based on the uncertainty principle itself, and it says that just let me attend one important message. So yes, let's begin. So this question says that in a series of experiments on the determination of the mass of a certain elementary particle, it is certain elementary particle, we are not sure, but the result shows a variation of variation of mass. Okay, so you are trying to calculate the mass, and the variation of the mass is plus minus 20 times mass of electron. So we know the mass of electron. Okay, now we are going to estimate the lifetime of the particle. So lifetime, your mind must think that okay, it is talking about time, and whenever there is time, we have the time energy relationship. Time energy, Heisenberg's uncertainty principle, and that is uncertainty in energy multiplied by uncertainty in time is greater than or equal to h bar upon 2. This is what we already know. So we don't have energy, but we have mass. But we have uncertainty in mass, and from mass, when we multiply C square, we actually get energy. So this is the simple question again, and we are going to introduce it like that. The uncertainty principle, formulated by Werner Heisenberg, states that two conjugate pairs which do not commute in quantum mechanics can never be precisely measured at the same time, that means simultaneously. In this case, it states that energy and time can be exactly determined simultaneously. Okay, in this case, okay, you just forget this line. This is garbage. Okay, so solution, given the mass uncertainty, that is, it is plus minus 20 times mass of electron, where me is mass of electron, we use the energy time uncertainty principle, which is this, as I have stated earlier. So this energy uncertainty can be related to the mass uncertainty through the equation E equals to mc square, and this is nothing but mass energy equivalence. Okay, so delta E would be delta m times c square, and you know that it is going to be from minus 20 me to plus 20 me, though, so whole range is 40 times me. So this is what we have used here. Okay, so using the uncertainty principle, and you plug in the all the ingredient, you will simply get that this delta t must be greater than or equal to h bar upon 80 me c square. Now it is the matter of calculation only. Use your calculator and you will find that it is minimum 1.61 multiplied by 10 to the power minus 23 second. So this is the lifetime of that particular elementary particle. We don't know what it is. Okay. So estimated lifetime of the particle based on its mass uncertainty is this much, 1.61 multiplied by 10 to the power minus 23 second. It decays via weak force into a nucleon and pion. This is extra information which I have provided you based on the fact that the time lifetime of such particle is 10 to the power minus 23 second. So it highlights the precision required in the high energy physics experiments and the stability of the lambda particle. So if you know that that particular unknown elementary particle could be lambda particle. Why? Because lambda particle have the similar lifetime, have similar lifetime of around 10 to the power minus 23 second. So this was again a simple question, and let me summarize you that we have mass. From mass we got energy, and from this energy we got delta T by using delta E times delta T is greater than equal to h bar by 2. So this is pretty simple mathematical question, but because it is subjective in nature, you need to write each and every step clearly. And by step, I mean arguments, like the well-known authors write in their book that they do mathematics minimum and they do arguments in the good amount of number. Now again, we have the same question that we are going to find the de Broglie wavelength of neutron and electron with kinetic energy having 500 electron volt. So whenever you get such question, let me tell you very clearly, you will just, for your first step would be to know that whether it is relativistic case or non-relativistic case. So in relativistic case, what you are going to check that whether it is greater than its the given energy is greater than its rest mass energy or not. The given energy is greater than its rest mass energy or not. So given energy is 500 electron volt, and rest mass energy of neutron is 939.6 million electron volt, which is far greater than the given energy. And given energy of electron is around 511 kilo electron volt. So it is also far greater. So both the case which we are going to solve here for neutron and electron respectively will be of the non-relativistic regime. So in non-relativistic regime, we are going to use what we have learned, that kinetic energy is p square upon 2. Okay. Otherwise, what we will have to do, we will have to do that we will be using E square equal to p square c square plus rest mass energy square. So this is the relativistic energy formula. But right now we are not required to use this particular formula. Again, the introduction goes as same. The de Broglie wavelength is fundamental concept AO and introduced by Louis de Broglie. It describes wave-like behavior of the particle, and it is inversely proportional to their momentum as we see in this particular formula. So a neutron with kinetic energy of 500 electron volt would have momentum given by this particular equation. So whenever you find the formula value of momentum by substituting all the constants, you are going to get this particular constant, and then by using the de Broglie wavelength, you are going to find that it is around 1.28 into 10 to the power minus 12 meter. So this is all about calculation. We have already learned the concept here that for the relativistic case, the rest mass energy must be comparable or greater than the given energy in the question. Now we are going to solve for an electron with kinetic energy of 500 electron volt. So again, we know that energy or kinetic energy is related to momentum by this particular equation, and in such a manner, you are going to get momentum to be 1.21 multiplied by 10 to the power minus 23 kilogram meter per second, and thus by using the same de Broglie wavelength relationship again, you are going to find wavelength of the electron to be 5.48 multiplied by 10 to the power minus 11 meter. Okay, so the conclusion goes as follows: the de Broglie wavelength of a neutron with kinetic energy 500 electron volt is this, and for the electron it is this, and these results illustrate wave particle duality of the matter. Just it. And let me tell you, writing introduction and conclusion will make your answer look more complete. Your answer would be more complete. So better marks. So better marks. So always follow this approach, and I hope you will be getting better marks in the mains examination. Now let's move to the next question, where the mean life of lambda particle is 2.6 multiplied by 10 to the power minus 10 second. So what will be uncertainty in the determination of its mass? So look, it is just a reverse of this question. We have just solved this question that we have got the uncertainty in its mass, and we are required to find the lifetime. Now we have the lifetime and we are going to find the uncertainty in its mass. So again, we are going to write the same introduction, copy paste it in this question as well. And we have the lifetime of 2.6 multiplied by 10 to the power minus 10 second. So we are going to use that in energy time uncertainty relationship, which is delta E times delta T greater than equal to h bar by 2. Now you are going to rewrite it in uh, in the term of mass. So we know that delta E is going to be delta M times C square. So we have written that delta M times C square, and from this we have got the answer, which is delta M greater than or equal to h bar upon 2 C square delta T. We know the value of H, we know the value of C and those all thing, and then we could simply find the determination of mass, but in electronic volt EV. Okay, so let me tell you. So this is the approximate relationship in electronic volt. Okay, so again we are just using your mass energy equivalence. Okay, so I think this is the good conclusion, and but I would like to improve it by using the term mass energy equivalence in our conclusion as well. So let us think of something better. So here the conclusion is already good, but we are going to make it better. The uncertainty in mass determination of the lambda particle is approximately this much, and and it also demonstrates mass energy equivalence. Done. Why mass energy equivalence? Because that particular term is used in the syllabus itself. Okay. And this is just the conversion that one electronic volt is 1.602 multiplied by 10 to the power minus 19 joule. So you just divide by that and you will get the term in electronic volt. Now we have next question. We need to find energy, momentum, wavelength of the photon which is emitted by a hydrogen atom, making a direct transition from an excited state with n equals to 10 to the ground state. So this is the transition from N2 to N1, where N2 is 10 and N1 is 1. Okay, so we know that the energy of such photon would be the energy difference for both the orbits. So energy difference could be calculated by this particular formula. We know that energy in the nth orbit is simply given by formula, which is minus 13.6 z square upon n square. Okay, so we for z is the atomic number, which is 1, so this will reduce to minus 13.6 z upon n square electron volt, 1 upon n square electron volt. And when you substitute this formula, you are going to get that the energy would be simply 13.464 electronic volt. Okay, so we are going to find now momentum and the wavelength. So if this is energy, so this would be the corresponding wavelength by using the relationship energy is equals to hc upon lambda. We know that energy is nothing but h times frequency, and frequency is c upon lambda. So this all are basic relationship which you must remember at any moment of time. Even in your sleep, if someone asks you what is that, you must blubber it instantly. So in that way, this is the value of the lambda, that it is approximately equal to 9.13 multiplied by 10 to the power minus 8 meter. And you are also required to find the recoil speed of the hydrogen atom in this process. So recoil speed obviously will depend on the momentum itself. So momentum would be simply for photon P equals to E by C. How? Let me tell you. So we know that energy, this is very basic expression of energy in the relativistic region. You must always remember it. Always remember it. Okay. So we know that a rest mass energy for photon is 0. So we have got energy equals to P square C square, and then P is simply E by C. So this is what we have used in the solution itself, and then you will get momentum to be this. And we know that once you get the momentum, you could get the recoil velocity by dividing that momentum with the mass itself. So this is the recoil velocity, and then you could finally conclude that photon emitted in the hydrogen atom transition has a wavelength of this much nanometer wavelength, that is 91.3 nanometer, and the recoil speed of the hydrogen atom would be approximately 4.3 meter per second. And this result illustrates the principle of energy. And this is for your knowledge as well. Suppose that you are not going to write that much information in the real examination itself, then just know this. This is the content enrichment or value addition, whatever you can call it. That we are not only solving the PYQ, we are also trying to learn something new. Okay. And this all thing have application in spectroscopy and quantum mechanics itself. Now let me tell you, an electron is confined to move between two rigid walls separated by 10 to the power minus 9 meters. So you need to compute the de Broglie wavelength representing the first three allowed energy states of the electron and the corresponding energies. So suppose that we have two rigid walls, this wall 1, this wall 2, and this is 10 to the power minus 9 meter. The electron can move only in between that. So if you know the basics of wave mechanics, then its wave function would be simply 0 here at the walls. Wave function would vanish. So this is your value enrichment. Okay. But this question is numerical in nature. We are how numerical? Because we are required to compute something. Okay. We are not required to describe, derive, demonstrate, or something like that. So we are required to compute. That means it is numerical in nature, and we could directly use the formula of energy for such one-dimensional box. 1D box. Okay. So let's introduce this solution. So the de Broglie wavelength is fundamental concept in quantum mechanics, which describes wave nature of particles. According to this de Broglie hypothesis, every moving particle or object has an associated wave. Okay. Why every moving particle? Because if you recall, it is h upon p, and momentum could be only true for the particles or something which do have some kind of motion. So the wavelength is inversely proportional to its momentum, and the concept was historically pivotal in the development of quantum mechanics. Okay, why? Because it proved wave-particle duality (WPD), wave-particle duality. So to solve for the de Broglie wavelength and corresponding energies, we will use the particle in a box model. Very clearly, we have written it that we are going to use particle in a box model. Here, the electron is confined in one-dimensional potential well with width 10 to the power minus 10 meter. So the energy level for the particle in the box are given by this particular formula, that is n square h square upon 8 ml square. And you are required to memorize this. Always know that this is what we are going to have. N is the principal quantum number, that is 1, 2, 3, and whatever. H is Planck's constant. M is the mass of the electron or whatever the particle we have confined in that particular box, and L is width of the box. In our case, this L is nothing but 10 to the power minus 9 meter or 1 nanometer. And we are going to compute the first three energy level. Then we will substitute n equals to 1, n equals to 2, and n equals to 3. For each case, we are going to get the energy by simply using the calculator. The first energy E1, that the energy of the first energy level would have value 6.03 10 to the power multiplied by 10 to the power minus 20 joule. For the energy in the second energy level would be 2.41, and for third it would be 5.43, and so on. So I think the energy calculation is correct. Okay, because energy is simply also equal to, for nth level, n square energy of the first level. We could get it from this particular relationship. So I hope we have got it clearly. So now you could also write the de Broglie wavelength, which is given by this particular formula. So Pn is the momentum of the electron in the nth energy state, and for a particle in a box, the momentum is given by this particular relationship. We know that. We have already calculated En. That is, we have already calculated E1, E2, and E3 in the previous page. So momentum for the first three state is simply this, this, and this. This is simple and pure calculation, nothing else. And whenever you substitute the value of the momentum, you will simply get the value of energies as well. Okay, and we have also plotted that. So these all are the plottings, and you should also, whenever there is a space or a time allowed or there is scope, you should always plot the graphs, schematics, diagrams, whatever is relevant for that particular question. So these values reflect the quantized nature of energy levels in a confined system. Okay, and these are significant in the fields of quantum computing and semiconductor physics. Now let's move to the last question of this particular video lecture. A typical atomic radius is about 5 multiplied by 10 to the power minus 15 meter, and the energy of the beta particle emitted from the nucleus is at most at the order of 1 million electron volt. So we know that nucleus, whenever there is some kind of nuclear activity, the beta particle is emitted. So we have measured the energy of that beta particle throughout our scientific journey, and we know that it at most it is around 1 million electron volt. So we based on this information, we are required to prove that uncertainty principle, as per the uncertainty principle, the electrons cannot be present in the nuclei itself. So let's start. The uncertainty principle formulated by Werner Heisenberg states that two conjugate pairs which do not commute in a quantum mechanics can never be precisely measured at the same moment, and so on. This is the Heisenberg's uncertainty principle, that is delta x multiplied by delta p is always equal to or greater than h bar by 2. Delta x is uncertainty in position and delta p is uncertainty in the momentum. H bar is a reduced Planck's constant and it is equal to 1.055 multiplied by 10 to the power minus 34 joule second. For an electron which is confined within a nucleus of radius r, the uncertainty in its position would be of approximately same size of the nucleus. So we are going to take this value itself for the uncertainty. We have already discussed it. Okay. And by using this particular uncertainty, we are going to find the uncertainty in the momentum. So this is the uncertainty in the momentum once we use the calculator. Okay, you are always going to use calculator. Practicing calculation on calculator is important. Practicing calculation on scientific calculator is important. Okay, so now we have got the momentum by and by momentum you can always find the energy, which is p square upon 2m. So energy is going to be around 381 million electron volt. So this is such an high energy which has been observed, which is around 1 million electron volt of the beta particle. We already know that beta particle is very energetic, and so if we are going to confine electron within the nucleus, then there should be something coming out from the nucleus during the decay process or some kind of nuclear process, which would have energy as great as 381 times the beta particle. That means we could conclude that we haven't found something that and that leads to the fact that electron cannot be confined into the nucleus because electron does not have that much energy. Okay, or nothing like that we have found till now. Okay, So the conclusion goes as follow that minimum energy for an electron confined within a nucleus according to uncertainty principle is approximately 381 million electron volt. This is significantly higher than the typical energy of the beta particle emitted from the nucleus, which is about 1 million, million electron volt. Thus, electron cannot be present in the nucleus as their confinement would require them to possess unreasonably high energy, inconsistent with the observed nuclear phenomena or nuclear decay, whatever you like to call it. So this is what we have solved. I hope we all have learned well, and we are here to inculcate the mindset, the complete 360-degree thought to solve and present, to solve and present the solution to meet most important factor called demand of the question. This will lead to maximum marks. So let's meet in the second lecture. So have a nice day. Bye. Take care.